Today we have another particle problem. This time the particle is going to be moving up and down along the y-axis rather than right and left on the x-axis. We're still drawing a graph that goes from left to right because we're not mapping the position, graphing the position at all. We are graphing the velocity of the particle. So what we want to do is tell the story of this particle in increasing detail. So here we have a graph indicating the velocity of a particle as it moves up and down the y-axis, with positive velocity indicating upward motion, and so negative velocity indicates downward motion. So we're looking at the derivative, and we're going to want to answer questions about the position and the acceleration of the particle. We're going to want to increase the level of detail. So the most basic thing that we notice is that for 3 seconds, the velocity is negative, and then for 2 seconds after that, the velocity is positive. So the most basic thing we can say is that the particle starts off moving down and then starts moving up. That's what we can see just based on this. The particle starting at 0, the particle So starting at y equals 0, because the velocity is negative for a while and then positive, we can see that the particle moves down and then the particle moves up. Now, this is not a lot of detail, but that is just generally what's going on. Negative velocities indicate going down, and then positive velocities indicate the particle is moving up. We can increase the level of detail because we know for how long the particle is moving down. The particle moves down for 3 seconds. And then moves up for 2 seconds. Or we could say moves down for t equals 0 to t equals 3, and then moves up to t equals 3 to t equals 5. We know that the particle is moving down because its velocity is negative for 3 seconds. And it's moving when it's moving up because the velocity is positive. So we can even add more detail. I had a plan for where I was going to write stuff, and I immediately abandoned it. No, I'm just erasing. Does it count as regret if you're just going to erase it and then fix it? I'm not sure. So we can even include the reasons why we're saying these things. So starting at y equals 0, the velocity, the particle moves down for 3 seconds, since the velocity is negative for t between 0 and 3, and then moves up for 2 seconds, since the velocity is positive for t between 3 and 5. Notice that t is equal when t is equal to 0 and when t is equal to 3, the velocity is equal to 0. So I didn't want to include 0 and 3 in when the velocity is negative and positive. But we can include more detail than this because we know more than this. So we can also include position, position information. The particle moves down and then moves up, but we can include more information. We can figure out how far the particle moves. So notice that we can calculate the area. The velocity is negative. We know that the position is decreasing because the velocity is negative, and the area will tell us by how much the position decreases. So if we look at each of these, if we just break this up into 3 pieces, anticipating that we're going to graph this later and find each of these areas. Here the area is -1, here the area is -2, here the area is -1. And then from 3 to 4, we have an area of +1, and from 4 to 5, an area of +2. The sign of the derivative tells us which direction the particle is moving. The area tells us how far. So we can include more information. So starting at y = 0, the particle moves down a total of 4 units in 3 seconds. And then moves up 3 units. So starting off at y = 0, the particle moves down for 3 seconds, a total of 4 units, and then turns around and moves up for 2 seconds for a total of 3 units. So now we know some more stuff. We know that the particle started off at 0 at 3 seconds. The particle was at -4. And then at 5 seconds, the particle was at -1. So we have now included position information. We can also calculate the acceleration of the particle at various times. For 1 second, the particle's acceleration was -2 centimeters per second, a constant -2 centimeters per second. So in that downward motion, from t = 0 to t = 1, the slope of the velocity was, here it is. The slope of the velocity was -2. So we'll say the acceleration of the particle was -2 centimeters per second squared. From t = 1 to t = 2. Oh, we can also include the acceleration was constant. We have constant acceleration. And that's why the graph is the velocity is a line. From t = 1 to t = 2, the acceleration of the particle was 0. So we know the acceleration of the particle because this is the slope of the velocity. The acceleration of the particle will be the slope of the velocity. That's the graph that we're looking at. The acceleration of the particle we would call it constant because the velocity is a linear graph. No, we could say the acceleration is the derivative of the velocity. Specifically, it's the derivative of the velocity with respect to time. But if you just said acceleration is the derivative of the velocity, everybody would know what you're talking about. The reason that I specifically said slope of the velocity is that we're making this based on reading a graph. So that's why I said slope instead of derivative. But that's a good question. Should we say derivative or is it okay to say slope? The reason it's okay to say slope is because we're looking at a graph. And the reason I can get away with saying slope is that that section of the graph is linear. So I can be a little bit lazy in my wording. But later on in this sentence, we do point out that we're dealing with a linear velocity because we mentioned the constant -2 centimeters per second squared. Once again, from t equals 1 to t equals 2, the acceleration, which is the slope of the velocity of the particle, is 0 centimeters per second. Because it's the acceleration is 0 centimeters per second, the particle is moving with constant velocity. So that 0 centimeters, that 0 acceleration means constant velocity. The velocity is not changing, so that's the acceleration being 0. And then from t equals 2 to t equals 4, the acceleration of the particle is a constant 2 centimeters per second squared. So it's not just from 2 to 3. I kept the same line going from t equals 2 to t equals 4. So we could say from t equals 2 to t equals 4. The acceleration of the particle was once again a constant, but this time positive 2 centimeters per second squared. And then from t equals 4 to t equals 5, once again, the particle is moving with constant velocity. So when you say constant velocity, you're saying acceleration is 0. with all this information, we can get a pretty good picture of what's going on with the particle. We can draw a graph of the location of the particle. We were told that the particle started its journey at y equals 0. So at 0 seconds, we'll start off at 0. What we already know is that it traveled down for 3 seconds, a total of 4 units. And then went back up a total of 3 units, so it'll end up at -1. But we can get more detail than that because we labeled all the different smaller changes in position. So in the first second, the particle was moving down and it decreased, its position decreased by 1. So 0 minus 1, it's at -1. From 1 to 2 seconds, it decreased by 2, the position decreased by 2. So it went from -1 down to -3. And then from 2 to 3, the particle decreased by, position decreased by 1 again to -4. The velocity was increasing, but the particle was still moving downward. It was just slowing down. Then at 3 seconds, the particle stopped moving down and started moving up, because from 3 seconds to 4 seconds, the change in position is +1. So we went from -4 up to -3. And then from 4 seconds to 5 seconds, the change in position is 2 centimeters from -3 to -1. So the area is telling us how much the position is changing. So now we can graph the position of the particle. If I start off here at t equals 0 at 0, at 1 we'll go down, be down 1. At 2 we'll be down at -3. At 3 we'll be down to -4. At 4 we'll be back up to -3, and then at 5 we'll be at -1. So you can see the graph spends all of its time below the t-axis because the y is always negative. Because the amount of decrease was greater than the amount of increase, we never got back to our start. There were 2 sections where the velocity was constant. If we have constant velocity, that means the graph of position will be linear. So constant velocity means linear position. Constant velocity means 0 acceleration, so no concavity. So between 1 and 2, oh, I didn't label my axis again. Between 1 and 2, we'll see linear position. And also between 2 and 4, linear position. Between 0 and 1, the acceleration of the particle was negative 2 centimeters per second squared. So since the acceleration is negative, our position graph will be concave down. So I'm not just going to connect the dot from 0, 0, 0 to 1, negative 1. I want to draw it concave down. When we had positive acceleration between 2 and 4, we should see the graph be concave up. So for positive acceleration, our position will be concave up. Now, on that section from 2 seconds to 4 seconds, the graph does change direction at 3. So we're drawing concave down, decreasing from 2 to 3, and then concave down, increasing from 3 to 4. So far as details go, notice that the graph that I drew is flat at 0 and at 3. The graph of the position is flat at t equals 0 and t equals 3. This makes sense because the velocity was equal to 0 at those 2 points. So here's a graph of the position, including all of its intervals of increase and decrease, the correct amounts of increase and decrease, and the correct concavity. That was it, with the correct concavity. I said that like there was going to be another phrase after that, and there wasn't. It's kind of like a stop in the middle of the sentence. We can also graph, if we want, graph the acceleration. It doesn't seem like an important thing to graph, but we do get some information out of it. So at the top of the page, from 0 to 1, the acceleration was a constant negative 2 centimeters per second. So I don't need a lot of graph here. So our graph of acceleration from t equals 0 to t equals 1, we have a constant acceleration, -2, because the graph of the velocity was a line, and the derivative is just going to be the slope. So from 0 to 1, we have a constant -2. From t equals 1 to t equals 2, the acceleration of the particle was 0. From 1 to 2, the acceleration is 0. And then from 2 to 4, the acceleration was a constant 2 centimeters per second. And then from 4 to 5, back to 0. So it's an important the important thing that we want to notice here is that the graph of the acceleration is discontinuous. That's one of the things that we want to notice. Note. The graph of the acceleration is discontinuous. We knew that this was going to happen when we looked at the graph of the velocity. The places where the acceleration is discontinuous, that's specifically at 1, 2, and 4. Those are the points on the graph of the velocity that the velocity was not differentiable. So it makes sense that the graph of the acceleration was discontinuous at 1, 2, and 4, because the graph of the velocity is not differentiable at 1, 2, and 4. So we are not surprised to see the graph of the acceleration being discontinuous at 1, 2, and 4, because the graph of the velocity was not differentiable at 1, 2, and 4. Any questions? So why is the acceleration equal to 0 between 1 and 2? So the acceleration is going to be the slope of the velocity. So between between 1 and 2, the velocity is flat, so the slope is equal to 0.
So if it's a straight line, then we say,
If it's a horizontal line, then the acceleration will be 0. If the velocity is a horizontal line, then the acceleration is 0. If the position is a horizontal line, then the velocity is equal to 0. Yes. At 5 seconds? Yeah, at 5 seconds, the particle is at -1. It's at -1 and it's moving up with a velocity of 2 centimeters per second, and unless something changes, at a constant velocity of 2 centimeters per second. So it's negative, but it's moving in the upward direction. Apparently at a constant velocity, at least before 5. So what we want to notice is not just the big picture. Particle moves down, particle moves up. We can determine how far the particle is moving in each of these cases and what the acceleration of the particle is. And each time we get more information, the graph of our position becomes more detailed. The original description was just like the particle moves down, the particle moves up. But there's more to it than that. It's not just moving down and then moving up. The first thing we did was it moved down 4 units and up 3 units. And then we started looking closer. We started including the acceleration information, the slope of the velocity, to get us the concavity of the graph. So we get more detail. Any questions? This particular exercise covers a lot of ground. I mean, think about all the things that we had to talk about here. We have the relationship between position, velocity, and acceleration. The relationship between function, first derivative, and second derivative. The relationship between concavity, direction, and sign are all in play here. Derivative stuff, because we're talking about derivatives, and integration stuff, because we're talking about area. So this kind of covers all the things that we have been talking about. How's everybody okay?
Yeah.
So all we have to do now is look at we have our velocity graph from yesterday. So we graphed the X yesterday and we graphed the Y today. So we've got one set of information about X and another set of information about Y. So rather than just trying to describe a pair X and Y, where the X and Y are related, I want to be able to describe X and Y independent of each other as functions of, say, some other variable, some parameter like t. So now what I want you to do is take your graph of X that you got yesterday and the graph of Y and plot those points together. Now that we have this, now we have 6 sets of coordinates. I've got points for X coordinates from yesterday, and I've got Y coordinates from today. Plot those points. The first one's at 0, 0 when t is equal to 0. And I can't remember the points from yesterday. But rather than writing Y as a function of X or writing an equation that relates X and Y together, I've got X and Y defined independently of each other. Draw that graph. These are parametric equations for the graph. So that's the new thing that you want to do. This would be for tomorrow, but there's no school tomorrow because holiday. Yeah, this is the Y. This is what Y looks like. Here are the values of Y. Then we want to go grab the graph and the table from yesterday. Those are your X coordinates. Combine your X coordinates to Y and Y coordinates and build a graph out of those. Any questions? I will most definitely erase this. Hopefully I'll scan it and put it in the notes. But on Monday, I will totally forget that I wanted to do parametric equations. So on Monday, I'll be standing up here for kind of a long time. And what's going on is I'm trying to remember what I wanted to do. And then I'm going to go, oh yeah, that's right. Any questions? All right, that's it for today. That's it for this week. I'll see y'all on Monday. We have good long weekends. And thanks for playing.